Hello everyone, this is a part 3 of Pinacol rearrangement. So in this video basically you will see that Pinacol type of rearrangement is also possible in epoxides, because epoxides are one type of dehydrated form of 1,2-diol. So we will see that it is also possible here. But I will request you to watch the first part 1 of Pinacol rearrangement, where you will get the basic idea of this rearrangement, and then it will be easier for you to understand this one. So let's quickly brush up what is Pinacol rearrangement. So it is 1,2-diol or vicinal diol where we do this type of reactions. Here in presence of H plus, OH is converted to some good leaving group, and now this lone pair, it will push this one of this group and it will migrate here. So here this leaving group is basically pulling this migrating group, and as if the lone pair over the other oxygen, it is pushing. So push-pull type of mechanism, and ultimately we are getting this type of ketone. Now epoxides are dehydrated form of 1,2-diol. Suppose if you are removing one H and one OH, basically you get epoxide like this, right? So when it is happening in epoxide in presence of Lewis acid. So in presence of Lewis acid, first this type of interaction between the oxygen, the lone pair is given to the Lewis acid, and one of these side, that is one of these carbon oxygen bond, is broken. Now that depends on in which side the carbocation is more stable, but here we have taken a symmetric molecule, so no problem. So carbocation is generated, and finally the lone pair that will be pushing one of this group and it will migrate here. So finally you will be getting this type of ketone. These are the Lewis acid that we can take. So this reaction here, carbocation intermediate in a Pinacol rearrangement, that you already seen in Pinacol rearrangement, that type of carbocation intermediate formation is also possible. It may not be always the fully formed free carbocation, but carbocation type of character will be generated. So it can also be formed from an epoxides, and when you are treating these epoxides with Lewis acid, it will promote this type of similar type of reaction. So here if you watch carefully, you will see the epoxide oxygen function as the leaving group. So as if this part is removed, so this is the leaving group, and this oxygen again it is becoming the new carbonyl group. So the oxygen which is interacting with Lewis acid, that oxygen is basically retained. There is no loss of oxygen. That in Pinacol we have seen one of the which is we have lost in the form of water, but nothing like that. So this oxygen, it is the leaving group, and it is also becoming the oxygen in the final product, the carbonyl compound. Fine. We will see some examples. So these examples you can find in Clayden, and the page number I will give in the description box. Please check there. So the first example, as you can see, we have taken, this is again a symmetric molecule in presence of very weak Lewis acid, magnesium bromide, MgBr2. We are getting first, there will be some interaction between these two, and ultimately we are getting in any one side, because both sides same, there will be some positive charge. Now this positive charge finally it will be pushing this pH. So among H and pH, this will be migrating here. So in the first part I have detailed discussed, that is a migratory capability. So pH and H, especially when it is H, there is no such ambiguous migratory order we can predict. It is difficult to give. So sometimes you will see pH is migrating, sometimes H, because it depends on so many factors. So to understand that, please check part 1. I will not discuss that here. So pH is migrating here, and ultimately we are getting this type of aldehyde. In the next example, here again we have epoxide, but now it is not symmetric. Now which side their carbocation will be stable? Obviously this side the carbocation will be stable. So there will be first interaction between these two, negative charge over BF3, and finally this side you have two hydrogen. So one of this hydrogen can be migrating when this electron is pushing it, and already this part is acting as the leaving group. It will also pull one of this H, so it will be migrating here. So again I am saying, even if the positive charge is not generated, that is free carbocation is not generated, but for the sake of understanding, if we write it in this way, it will be easier for us to understand. That is why I have drawn in this way. So finally we are again getting aldehyde. Example number 2. The next example is very interesting. Why I am saying so? Just focus on this epoxide. It is symmetric, fine. Now in the left hand side we have RLi, and in presence of RLi you are getting normal addition product of epoxide that is expected, as if this R is attacking here, and in presence of H plus there will be OH. Very that is expected, right? But in presence of RMGBr, Grignard reagent and H plus, it is completely a different product we are getting. Now what is happening here? To understand that, let's forget this reaction for some time and take the original substrate and instead treat it with magnesium bromide. So this is a very weak Lewis acid. In presence of this weak Lewis acid, first of all there will be this type of interaction, and one side you can break the bond. It is symmetry, you can break the bond. Now if you observe the numbering, finally what is happening, this lone pair, it is pushing, and this part is acting as the leaving group, so it will pull. So one of this bond, CC bond, so here 1,2 bond, as if it is migrating, and ultimately there is a new bond, 2,6 bond is generated. So 2,1 bond is broken, 2,6 bond is generated, you are getting ring contracted product. So here hydrogen is not migrating, CC bond is migrating. And once this aldehyde you are getting, now we can get some clue why with Grignard reagent we are getting this type of product. So what is happening here? With a Grignard reagent, rearrangement occurs faster than the addition of the epoxide. So if it is rearrangement, that is in presence of RMGBr, if it is rearrangement, first you will get this product, I am writing here rearrangement. And once this rearrangement is already occurred in presence of RMGBr, now the normal addition. So R here it will attack here, and ultimately you will get this type of addition product. So when you are treating it with Grignard reagent, unlike RLI, here first rearrangement will occur just in presence of MgBr2 you have obtained, but after that, once the aldehyde is produced, now it will behave as it is. So this product, suppose this product I am writing here as P, so this is the product you will get after the rearrangement of the epoxide, that is this one I am talking about. First there will be rearrangement in presence of this Grignard reagent, followed by the addition of RMGBr2 aldehyde. So to understand the product of RMGBr, we have taken the clue of the reaction when it is occurring in presence of MgBr2. So it will behave just like MgBr2, that is RMGBr, it will behave like MgBr2. It will give first the product that you are getting from MgBr2, but it will not stop here, because ultimately RMGBr, now it will attack this carbonyl carbon of this aldehyde, and you will be getting the addition product. So this is also taken from Clayden. You can I will give the page number, you can check it. Next example, here we have epoxide, and in the left hand side we have methyl and pH, right hand side we have CO2 Et and H. In presence of Lewis acid, suppose carbon number 1 and 2. Positive charge at carbon number 1 is more stable. So that is why we have drawn only one carbocation. Other side we have not drawn the other possibility. Now the question arises whether H will migrate or this will migrate. See, first we will check if hydrogen is migrating, what is happening. So if hydrogen is migrating, you are getting this new carbocation, and ultimately there will be C double bond O, Lewis acid will be removed, and CO2 that will be CO2 will be retained, right? But see, this carbocation, suppose this is carbocation number B, and we will see the other carbocation which you are getting by the migration of CO2 Et. So this carbocation is A. So carbocation A and carbocation B, if you observe carefully, A is more stable, because in the B carbocation you have electron withdrawing group, which is making this carbocation very unstable. So though it seems very unusual that CO2 it is migrating, not hydrogen, because what is the driving force? Because after CO2 it migration, the carbocation that you are getting, that is more stable. So based on that factor, this path is basically accepted, this is not. And the product that you are getting, this that is only by this type of mechanism you can explain why that product is formed. So finally there will be C double bond O, BF3 will be removed, and you will be getting this type of aldehyde. And if you see the configuration here, MEPH, that is again below the plane, pH is above the plane, and as if this bond is just changed by a CO2 Et. So it is same. So here we can say this statement that a single enantiomer of the epoxide rearranges with Lewis acid. Single enantiomer of the epoxide means I am talking about the initial substrate. So after Lewis acid catalysis, we are getting here a single enantiomer of the product. So if you want to understand how we are getting this product starting from this S, from S to P, how are we are getting this product, this explanation is applicable. Here we have a ketene molecule because CC double bond, C double bond O both are present. In presence of MCPBA, metachloroperbenzoic acid, first we will generate this epoxide. Once this epoxide is generated, now we will see the Pinacol type of reaction in epoxide. So this is a strained ring. So it will break. This CO bond will be broken and there will be positive charge generation and at this carbon, and now this is stable. But see, here further migration is possible, and because after all, though it is C plus and there are two alkyl group, but after all there is a C double bond O. So it will be not very stable. So now if one of these methyl group is migrating here, after methyl migration, you are getting a new positive charge at 4 position. So let me do this marking here also. 4, 3, 2 and this is 1. Now this one oxygen, it will attack here. So 4, 3, 2, 1, you will get a 4-membered ring. So this is our final product where you can see this is the connection point. And at 3 position, you are having tertiary butyl group and a methyl group. Methyl group, tertiary butyl group. So we have already reached the end point of this video, and I will leave the session with a hope that this video will be useful to you. Thank you all.